Good morning, everyone. Today I am here for infrared absorption spectroscopy. Introduction. Infrared absorption spectroscopy concerns the absorption of radiation in infrared range and is probably the single most widely used method of investigating the structure of organic substances. The instrument used for recording the infrared spectra is known as infrared spectrophotometer. The infrared region of electromagnetic spectrum range from 0.8 point 0.8 to 200 micrometer. 12,500 to 5 centimeter inverse, but most of infrared spectrophotometers has a range of 2.5 micrometer or a 4,000 centimeter inverse to 7.2 micrometer or 580 centimeter inverse. The infrared region between 0.8 point 0.8 and 2.5 micrometer is generally known as near infrared, and that between 15 and 200 micrometer is known as far infrared region. Since the organic molecule rarely undergoes absorption of radiation in the near and far infrared region, these are seldom used for spectroscopy purpose. The various absorption bands in an infrared spectrum are referred to either by the wavelength or a wave number of a radiation absorption. Band intensity is expressed in terms of absorption or transmittance, the two between related to each other. A is equal to log 1 by T. Basic theory of IR spectroscopy, molecular vibration. The most constituting a molecule are not held readily in fixing position. They are continually rotating and vibrating in a number of ways. To have an idea of molecular vibration, let us compare a bond between two atoms in a molecule to a weightless spring connecting two balls together. Just as the spring can be compressed or stretched or bent, the bonds can be stretched or bent, giving rise to vibration in a molecule. These are two kinds of molecular vibration. They are stretching and bending. They are described below. Stretching vibration or bending bond strength, bond strengthening. Stretching. In a simple diatomic molecule A, B, the only vibrating which can occur is a rhythmic compression and extension along AB bond. This type of periodic back and fro movement of atom along the covalent bond axis, which can be compared to that of a coil spring, is known as stretching vibration or bond stretching. Type of stretching. In triatomic or higher molecule, the stretching vibration can be two types. First, symmetrical stretching is it is the stretching vibration in which the movement of atom with respect to central atom in a molecule in the same direction. In other words, all the bond to the central atom are either stretched or compressed stimulatively. Second, asymmetric stretching. It is the stretching vibration in which one atom moves toward the central atom while other move away from it. In other words, one bond is being stretched and the other is being compressed. Bending vibration or deformation. In triatomic and higher molecular, there can be another type of vibration involving change of bond angle. Such vibration movements are referred to be bending vibration or deformation. Bending vibration may be depend as periodic change in bond angle between bond formed formed by two atoms with a central metal atom. Type of bending vibration. Bending vibration can be of four types. Scissoring. This is an in-plane bending vibration in which two atoms move toward each other. Second, rocking. This is an in-plane bending vibration in which two atoms move in the same direction. Third, wagging. This is an out-plane bending vibration in which the two atoms move stimulatively either above or below the plane with respect to central metal atom. Fourth, twisting. This is an out of the plane bending vibration in which one atom move above the plane while the other move down the plane with respect to central metal atom. Scissoring and rocking represent in plane bending while wagging and twisting represent out of plane bending. The different type of vibration in a molecule are very important for structure determination in infrared method. It may be noted that the bending vibration require less energy than stretching vibration because it is easier to bend a bond than it to its stretch. Principle of IR spectroscopy. We know that atoms constitute a molecule are not held rigidly in fixed position. They are continuously rotating and vibrating in a number of ways. The various modes of vibration possible in a molecule depend primarily on the nature of a bond themselves and to some extent on the molecule, on the nature of entire molecule. Absorption of infrared by a bond increase the amplitude of vibration and also being change in rotational energy level. However, in infrared range usually studies 2.5 micrometer to 15 micrometer, the absorption energy being about predominant change in a vibrational energy level. It is obvious that a given bond or a part of molecule can be absorbed only the wavelength of infrared radiation, which will provide the photons of that particular amount of energy which is required to raise the vibrational energy level to a permitted value. As the infrared radiation of a specific wavelength is absorbed and an absorption signal is produced. The infrared spectroscopy is based upon the wavelength is absorbed and absorbed signal is produced. The infrared spectroscopy is based upon the absorption of infrared radiation by the molecule in accordance with the quantization of this vibrational energy level. It should be noted, however, that all the bonds in a molecule are not capable of absorbing energy level. Infrared energy, the recording of amount of infrared radiation of different wavelength absorbed to raise the vibrational energy level constitute the infrared spectrum of a molecule. Figure 1.4 shows some of the stretching and bending vibration possible for an alcohol group and the character wavelength absorption due to these vibration. A wavelength range is given for each of these vibrational because the actual value will also be determined by the nature of a rest of a molecule. Unit in IR spectroscopy. The position of absorption of infrared in IR spectroscopy is generally expressed in terms of wavelength or in terms of wave number. However, the wave number is usually treated as absorption band frequency. The wave number corresponding to wavelength of infrared range usually studied are from 400 centimeter inverse to 667 centimeter inverse. Calculation of vibrational frequency, Hooke's law. The molecule of organic compound usually contain many carbon single bond carbon and carbon single bond hydrogen bond and also some other bonds. Therefore, the analysis of various mode of frequency for a molecule is very difficult because all the atoms present in the central molecule contribute to the vibrational modes. However, it is a strength possible to calculate approximately which a particular vibration mode will appear in the infrared spectrum by considering each bond present in a molecule at once at a time and ignoring the other bond. Let us, for instance, consider the stretching vibration of two bonded atoms. The stretching vibration can be compressed to oscillate the two balls connected to a, a spring which while the balls represent the atom and the spring represent the bond. As such, the value of a stretching vibrational frequency of a bond can be calculated fairly accurately by the application of Hooke's law, which may be represented as nu is equal to 1 by 2 pi under root k by nu, where k is the force constant which is related to the strength of bond. Nu is the reduced mass in gram per atom of diatomic system. It is calculated from the expression nu is equal to m1 into m2 divided by m1 plus m2, where m1 and m2 are actual mass of two atoms in a gram. Since nu bar is equal to nu by c, where c is the velocity of light, Hooke's law may be also expressed in nu bar is equal to 1 by 2 pi c under root k by mu. Hooke's law. If a body of a mass m is hung on a spring and given a pulley downward, it being to undergo simple harmonic motion. According to Hooke's law, the force which tends to restore the body to its original position is proportional to the displacement of a body from that position, that is F is equal to minus kx, where k is called the force constant of spring. The spring will have a definite frequency of vibrational frequency which is given by relation nu is equal to 1 by 2 pi under root k by m. If body of mass m1 and m2 respectively are connected by a spring, the vibrational frequency of spring is given by a relation nu is equal to 1 by 2 pi under root k by mu, where mu is equal to m1 m2 divided by m1 plus m2 is equal to reduced mass of a system. When two atoms held together by a bond are compared to the above relator, the vibrational frequency of a bond nu can be calculated by applying the same relationship as given above. Factor which determine the vibrational frequency. The simple analog between two bonded atoms and a simple oscillator help us in knowing the frequency of various absorption band in the infrared region from the nature of atom and strength of a bond between them as is related below. First, the smaller the mass of bonded atom, the smaller is the reduced mass and therefore higher the value of vibrational frequency. In other words, vibrational frequency is inversely proportional to reduced mass. The mass between a hydrogen and other atom has the highest known fundamental frequency, but covalent compound of halogen or most metals show infrared absorption of very low frequency which are too low to record on a routine spectrophotometer. Second, the force constant is a measure by a strength of bond and therefore the value increase with the increase in a bond order. It is take place as approximately 5 into 10 raised to power 5 dyne centimeter inverse for a single bond between any two atoms. For double or triple bond, the value are 10 into 10 raised to power 5 and 15 into 10 raised to power 5 dyne centimeter inverse respectively. In SI system, the value of K are approximately 500 Newton meter per meter, 1000 Newton per meter, and 15 Newton per meter. With the increase in the value of K corresponding to the increase in a bond strength, vibrational frequency also increase. In other words, vibrational frequency is directly proportional to bond strength. It must be noted, however, that the intensity of absorption depend most on the polar of the bonds. Simplifying for Hooke's law, for computing the value of nu bar, a simplified for Hooke's law may be obtained as follows: actual mass of an atom is equal to gram atomic mass of an atom divided by 6.02 into 10 to the power 23 Avogadro number gram, where 6.02 into 10 raised to power 23 is the Avogadro number. Number of fundamental vibration. It has been stated earlier that the absorption of a infrared radiation having energy equal to difference between two vibrational energy level will lead to the vibrational transition. In this, the transition from ground state to first excited state, light is absorbed strongly, and as a result, intense band called fundamental absorption band are produced. The number of fundamental absorption band exhibited by a molecule is related to the fundamental way of vibrating or a vibrational mode available to a molecule. In generally, number of fundamental absorption band, number of fundamental vibrational mode. Since a diatomic molecule has only one fundamental vibrational mode, such that stretching vibration since a diatomic molecule has only one fundamental vibration mode, stretching vibration, it gives rise to one fundamental absorption band. However, a polyatomic molecule can have more than one kind of vibrational moment. They exhibit more than one fundamental absorption band as given below. First, non-linear polyatomic molecule. It has been found that a non-linear polyatomic molecule can have 3 n-6 mode of fundamental vibration, where n is the number of atoms present in a molecule. For example, water. N is equal to 3 has 3 vibrational mode, 3 into 3 minus 6, each of which can give any absorption band. B. Non-linear atomic molecule. A linear atomic molecule has an atom can have O3 and minus 5 fundamental vibration for each carbon. For example, carbon dioxide N is equal to 3 has a 4 vibrational mode such that 3 into 3 minus 5. In case of larger molecules, the number of fundamental vibration goes on increasing very rapidly with increase in a value of n. but it has been observed that the number of fundamental bond actually obtained is usually less than expected from the theoretical number of fundamental vibration. This may be due to the following reason. First, some of fundamental vibration may be very weak and therefore may not be recorded as band. Second, some of fundamental vibration may be very closer and as a result overlapping of a bond may take place. Third, some of fundamental vibration may involve energy change which fall outside of a usual IR range. It is also interesting to note that the sometime additional band such as combination band, different band and overtone may also be exhibited. Selection rule. Most of molecules possess dipole moment due to the presence of polar bond linking the constituent atom. When a polar bond undergoes stretching vibration along the intermolecular axis, a change in electron distribution of a bond takes place. As a result, dipole moment also undergoes a change. In other words, a vibration produces a fluctuation dipole moment. Interaction between the oscillation dipole moment and the infrared radiation lead to the absorption of energy from the radiation, so that the energy of vibrational increase such that amplitude of oscillation increase. This interaction and absorption of energy can occur only in dipole moment at one extreme of the vibration is different from the dipole moment at other extreme of the vibration in a molecule. It is the evidence from the above discussion that a bond vibration can lead to the absorption infrared radiation only if it is accompanied by a change of a dipole momentum. As a result, comprehensive study in the field of spectroscopy, certain generalization has been made which determine whether a vibrational mode be effective for a particular type of spectrum or not. These are known as selective rule. For infrared spectrum, the rule is the only those vibrations are effective in causing absorption which are not centrosymmetric, such that the vibrations are not symmetric about the center of molecule. For example, symmetric stretching vibration of CO2 are centrosymmetric and are not effective in infrared spectroscopy, while the asymmetric stretching vibrations are not centrosymmetric and give rise to absorption in infrared region. Since most of the functional group in organic chemistry such as C double bond O, H bond, NH bond undergoes vibrations which are not centrosymmetric, they respond very well to infrared spectrum. Position and intensity of band. First, position of a or absorption band depend upon the type of bond present in molecule. Vibration wavelengths are found to be absorbed in the infrared spectrum of a molecule, giving rise to absorption band. The position of a absorption band depend upon the nature of a bond or a group. Absorption band characteristic of a particular bond or a group indicate the presence of that bond or a group in a molecule. For instance, in the spectra code in figure 2.6, the absorption band 3 micrometer 3333 centimeter inverse clearly establish the presence of a hydroxyl group in the molecule. Similarly, the presence of characteristic absorption band of a bond or a group guarantees the absence of that particular bond or a group. It may be noted, however, that the actual absorption pattern of a bond or a group may vary slightly from one type of a molecule to another. This is because the exact position or position of a absorption band is also determined to a very small extent by the nature of the rest of a molecule. Infrared spectrum can be usually dividing into two regions for the purpose of interpretation. First, functional group region in a generally absorption band from 2.5 to 8 micrometer or 4,000 to 1250 centimeter inverse are associated with the change in the vibrational state of a various bonds. Accordingly, this region is the characteristic of a type of bond present and may be termed as the functional group region of infrared spectra. Fingerprint region. Absorption band in the region 8 micrometer such that less than 1250 centimeter inverts are generally associated with complex vibration and rotational energy changes of molecule as a whole. This region is very useful for establishing whether two compounds are identical or different from each other. It is therefore referred to as the fingerprint region. There are so many absorption bands in the fingerprint region that no two compounds, however closely related, can have identical IR spectra in all detail, including intensity. On the other hand, if two given sample has exactly the same infrared spectra, it is conclusive proof of identity of two samples. Intensity of absorption band. Different absorption band in infrared spectrum has a different intensity. The intensity of absorption band is mainly depend on the magnitude of a change in dipole moment. The more the polar character of bond, the greater the change in a dipole moment and greater the intensity of absorption. For example, a carbonyl group has a much higher dipole moment than carbon double bond bond, and therefore it give rise to stretching absorption band of a much higher intensity than carbon double bond carbon stretching absorption band. The intensity of absorption band also increased to a small extent with the increase in the concentration of a molecule in the sample and the nature of absorbing group in a molecule factor involving vibrational frequency influencing. We have seen that the probability frequency of bond in its IR spectra can be calculated with the help of Hooke's law. However, it has been found that the calculation value for a bond is only in a tolerable agreement with the experimental value but never equal to it. This is because the vibration of each group is influenced by the structure of a rest of a molecule in its intermediate neighborhood. The important factors responsible for vibrational shift are as followed. First, electronic effect. When the substituent in a neighborhood of a particular group are changed, it brings about change in absorption frequency of that group due to electronic effect such as inductive effect and resonance effect. Due to these effects, the force constant or a bond strength are changed cause the absorption frequency shift from the normal value as illustrated below. First, inductive effect. The presence of alkyl group in the vicinity of a particular group cause plus I effect. As a result, the bond length of that group tends to increase or the bond strength decrease. Consequently, the force constant is lower and the frequency of wave number of absorption decrease. This is clear from the following example showing the absorption wave number of a carbonyl group is different compound. It is obvious that greater the plus I effect, smaller the wave number. If on the other hand, a group having minus I effect is present in neighborhood of a particular group, it increases the value of a force constant as a result of the absorption shift to higher value number, as shown below in a term of absorption wave number of a carbonyl group in acetone, chloroacetone and dichloroacetone. It is apparent that greater the minus I effect, higher the wave number. Third, resonance effect. Resonance effect has a significant influence on the absorption frequency or a wave number of ethylene bond in a conjugated diene and of a carbonyl group in conjugation of a group so that its bond strength decrease. This is turned downward the low force constant of a bond and the absorption frequency decrease. This is evidence from the absorption frequency of a C double bond O strength in the following compounds. It may be noted that in case of compound where both the resonance effect and the inductive effect operate but in opposite direction, the resonance effect may be dominant over the inductive or the reverse may be true. For example, in acetophenone conjugation take to lower the absorption frequency of carbonyl group stretch while minus I effect tends to increase the value. But resonance effect dominate the minus I effect so that there is a decrease in absorption frequency. Hydrogen bonding. The infrared spectra of organic compounds such as alcohol, phenol, carboxylic acid and amines which exhibit hydrogen bonding are strongly influenced by the presence of hydrogen bonding. Hydrogen bonding results in the weakening of the bonds involving so that E force constant decrease and absorption shift toward lower frequency or wave number. Some important generalization about the role of hydrogen bonding in infrared spectroscopy are as follows. First, the stronger the hydrogen bonding, the greater. Intermolecular hydrogen bonding give rise to a broader band, while intramolecular hydrogen bonding give rise to sharp and a well-defined band. Third, the intensity of absorption band in intramolecular hydrogen bonding is concentrated, depend, and decrease with dilution. In contrast, concentration has no effect on intensity in case of intermolecular hydrogen bonding because it takes place within the same molecule. Fourth, the downward shift is more pronounced in case of intermolecular hydrogen bonding than in intramolecular hydrogen bonding. Let us illustrate the above generalization with example. First, alcohol and phenol. In case of both alcohol and phenol, the free OH group give rise to the stronger absorption band in the region 3650 to 3600 centimeter inverse. On the other hand, hydrogen bond OH give broad absorption band in region 3400 to 3200 centimeter inverse. Second, carboxylic acid. Carboxylic acid generally exists as a dimer having strong intermolecular hydrogen bonding. Due to large strength of hydrogen bonding, there is a large decrease in absorption frequency of a carbonyl and OH group frequency in their dimer. The other carboxylic acid dimer exhibits a very broad band due to OH strength at 3000 to 2500 centimeter inverse as compared to about 3600 centimeter inverse for free OH group. Similarly, there is a downshift for carbonyl stretch in acid for about 1750 centimeter to about 1700 centimeter for a dimer form. Third, amines. Due to relative weaker hydrogen bonding in amines, the downward shift is in the absorption frequency of NH bond is only for about 35 centimeter inverse to about 30 centimeter inverse. Thus, this is much lesser than in case of OH bond in alcohol and carboxylic acid. Third, vibrational coupling. It has been observed that in some group containing two or more similar atoms bonded to a central atom, the absorption frequency of a bond is different from that of the isolated bond of the same type. This is because to mechanical interaction between the stretching vibrational of a bond known as vibrational coupling. For example, an isolated CH bond has only one stretching frequency, but a CH2 group which has two CH bond involving a common carbon atom show two different frequencies, each of which occur at a different value as compared to isolated CH bond. This is because the stretching vibration of a two CH bond in a CH2 interact with each other in two different ways, asymmetrical stretching and symmetrical stretching, to give rise to a coupling vibration. Due to symmetrical stretching, the absorption takes place at a higher value number to 2960 centimeter inverse, while symmetrical stretching shifts the absorption to lower wave number 2850 centimeter inverse than the isolated bond. Similarly, CH3 group and NH2 group and NO2 group and carboxylic ion show coupling vibration due to asymmetrical and symmetrical stretching. Instrument mechanism of recording the IR spectra. In an infrared spectrophotometer, the sample of a substance under investigation is placed in a beam of infrared radiation. The relative intensity of transmitted and therefore absorption radiation is automatically measured and plotted on a graph shown intensity of a transmission or absorption as a function of a wave number or a wavelength of infrared radiation. A simplified diagram of a commonly used infrared spectrometer is shown in figure 1.5. It consists of the following part. First, source of infrared radiation. A common source of infrared radiation is the Nernst glower, which consists of a mixture of G-chromium oxide, yttrium oxide, Ber oxide heated electrically to about 1775 Kelvin. Infrared radiation can also be produced by heating a rod of silicon carbide glober electrically. The beam of infrared radiation is split into two beams. One beam pass through the sample cell while other pass through the reference cell, which contain only the solvent. The two beams are allowed to enter the monochromatic by means of a rotation mirror. Second, sample container. The sample under examination may be employed in gaseous, liquid, solid, or solution form. However, solid scatter the radiation too much if placed in the path of a light directly. As such, they are either dissolved in organic solvents such as CCl4, CH3Cl3, or CS2, or ground with indole, liquid paraffin to form a mule, or converted into a pellet with potassium bromide. The sample containing and the optical part of a spectrometer are made of a rock salt or a certain other alkyl matter halide such as CSI, since glass is opaque to infrared radiation. Third, monochromator. By means of prism or diffraction grating, the monochromatic allow radiation of only one frequency to enter the detector at a time. The frequency of radiation get automatically vary. Fourth, detector. The detector scan the range of IR frequency required from the monochromatic and transforms the energy of radiation received into an electrical signal. This signal is proportional to the difference in the intensity of radiation in the sample and reference beam. Fifth, recorder. The recorder signal is automatically recorded on a chart paper showing intensity of transmittance as a function of wavelength or frequency of infrared radiation. In actual practice, it is a transmitted light from 0 to 100%, which is plotted in infrared spectra. For recording the infrared spectra, a very small amount of sample is needed, but the sample used must be absolutely dry because water gives strong absorption near 2.7 micrometer or 710 centimeter inwards and near 6.15 micrometer or 1630 centimeter inwards. These absorption may overlap absorption due to sample being analyzed. More sophisticated and sensitive spectrometers are now available and are generally replaced the instrument used earlier. One such spectrometer is a Fourier transformer infrared FTIR spectrometer, which has a much better sensitivity and take only 1 to 2 seconds for recording the spectra. The infrared spectra of ethanol is shown in figure 1.6. It depicts clearly the absorption band, which results the stretching and bending of a carbon hydrogen and oxygen hydrogen and oxygen carbon bond. It may be seen that infrared spectra, the peaks are upside down. This is due to the operational technique used in infrared spectrophotometer. Characteristic of absorption region of various bond. The characteristic infrared absorption region of various type of bond and functional group are collected in a form of table called correlated table. Table 1.1 is a correlated relationship of a data of absorption pattern of some important bonds and functional group. The letter S, M, W, V denote whether the intensity of absorption is strong, moderate, weak, variable. It would be remembered, however, that the table give only the approximate position of absorption band. But as already stated, the exact position of absorption band of a particular bond depend upon actual moment, molecular environment. Some character infrared absorption region. CH bond type of compound alkane give wavelength 3.3 to 3.51, frequency or wave number give 2850 to 2960 centimeter, intensity medium to strong, and so on. Spectral feature of some classes of a compound. Having discussed the fundamental concept of infrared spectroscopy in the previous session, we now take up the spectral feature of some classes of compound. Hydrocarbon alkanes. Infrared spectrum of alkane are generally quite simple and not informative because alkane do not contain any functional group. The most common peak exhibited by alkanes are given below. CH3, CH2 and CH group present in alkane give rise to CH stretching absorption. CH3 and CH2 also exhibit bending or deformative band in region 1470 1430 centimeter inwards. Carbon single bond carbon are less characterized and they are responsible for weak band in the region 1300 to 800 centimeter inverse. The main feature of spectra of alkane are summarized up in table 1.2. Second, alkene. Infrared spectra of alkene show many character absorption which can be very useful in structure determination. The most prominent peak is the vinylene stretch at slightly greater than 3000 centimeter inverse. The actual position depending upon the extent of substitution in alkenes. Carbon double bond carbon stretching vibration give rise to band of variable intensity at 1680 to 1620 centimeter inverse. Conjugation shift the position to lower frequency and increase the intensity of absorption. The important absorption band are summarized up in table 1.3 for alkenes. Third, alkynes. They exhibit strong absorption band for CH strength near 3300 centimeter inverse and another intensity bond CH bending at 650 to 610 centimeter inverse. A weak carbon triple bond carbon stretching absorption band occur at 2160 centimeter inverse. The band is more intense for terminal alkyls than non-terminal alkyls. Fourth, cycloalkanes. Cycloalkane exhibits mainly CH stretching absorption band. The reason of absorption move to higher value with the increasing in angle strain. For example, CH stretching of a cyclopropane is at 3050 centimeter inverse while that the cyclohexane is an 2990 centimeter inverse. Fifth, aromatic hydrocarbon. These compound exhibit CH stretching absorption of 3500 to 3000 centimeter inverse and C slightly double bond stretch absorption at 1600 1450 centimeter inverse. They are four prominent carbon slightly double bond stretching band at 1600 centimeter inverse 1580 centimeter inverse 1500 centimeter inverse and 1450 centimeter inverse. Absence of these bands means that the compound is not aromatic. These are also a number of carbon hydrogen banding band at 900 to 700 centimeter inverse. The actual number and position of these band depending upon the extent and position of a substituent of a aromatic ring. Hydroxyl compound. First, alcohol. The OH functional group of alcohol give a characteristic OH stretching absorption band in the infrared spectra. But as we might expect this absorption is slightly significantly influenced by hydrogen bonding. If there is no hydrogen bonding, an alcohol give a sharp variable at 3640 to 3610 centimeter inverse in the associated state involving intramolecular hydrogen bonding. A strong broad band appear at 3400 to 3200 centimeter inverse. In case of intramolecular hydrogen bonding, the OH stretching band appear at 3570 to 3450 centimeter inverse and is of variable intensity. In addition, alcohol also exhibits a strong and broad band in the range 1200 to 1000 centimeter inverse due to CH stretching. The exact location of a band depend upon whether the alcohol is primary, secondary or tertiary. Therefore, it can be used to determine the class of alcohol. The complete structure of alcohol of a course exhibits other absorption band as well due to the presence of other structural units such as carbon single bond carbon and CH bond. This is quite evident for the IR spectra of ethyl alcohol showing in figure 1.6. Second, phenols. As in case of alcohol, phenol exhibits a stronger band due to OH stretching in the range 3600 to 3200 centimeter inverse. However, the CaO bond stretching in phenol appears in a higher region as compared with alcohol. Infrared of a paracerol is shown in figure 1.7. Ethers. The infrared spectra of ether are characterized by a strong absorption band in the region 1300 to 1000 centimeter inverse due to CH stretching vibration. Alkyl ether show a single absorption in the region 1150 to 1060 centimeter inverse. Aryl and vinyl ethers exhibit a strong band in a region 2575 to 1200 centimeter inverse and a weaker bond in the region 1200 to 1075 centimeter inverse. The CO bond stretching absorption band of ethers are similar to that of alcohol, carboxylic acid, and esters. However, ethers can be distinguished from alcohol by the presence of OH stretching at 3600 to 3200 centimeter inverse. Similarly, ethers can be distinguished from carboxylic acid and esters by the absence of carbonyl stretching absorption at 1770 to 1680 centimeter inverse. Aldehyde and ketones. The infrared spectra of aldehyde and ketone are generally used in detecting the presence of these compounds. The carbonyl group in these classes of compounds showing a strong carbonyl stretching band around 1700 centimeter inverse. The actual position the band depending upon the nature of group attaching to the carbonyl group. First, aldehyde. The position of carbonyl stretching absorption band in aldehyde varies slightly according as the aldehyde is saturated aliphatic aldehyde or aromatic aldehyde or alpha beta unsaturated aldehyde. Further, the presence of electron releasing group shift the absorption to a lower value while the electron attaching group shift the absorption to higher value. In addition to carbonyl groups, carbonyl stretching band aldehyde show characteristic CH bond near 2820 centimeter inverse and 2720 centimeter inverse. Generally, the band near 2720 centimeter inverse is seen at and it is very useful in distinguish aldehyde from ketone. Infrared spectrum from N-butyraldehyde is shown in figure 1.8. Second, ketone. The carbonyl stretching band in ketone appear at a lower frequency or a wave number as compared to aldehyde due to large plus I effect operate in ketone. The carbonyl stretching absorption take place at still lower value for aromatic ketones and alpha beta unsaturated ketone. In case of cycloalkanes, the position of a carbonyl stretching band depend upon the size of a ring. As the size of a ring decrease, the absorption shift to higher value due to increase in angle strain. Infrared spectra of ethyl methyl ketone is shown in figure 1.9 for the sake of illumination. It must be emphasized that a carbonyl stretching bond is also given by carboxylic acid and their derivatives. However, these compounds also show certain other bonds which help to distinguish them from aldehyde and ketone. For example, carboxylic acid also show a broad OH band in the region 3000 to 2500 centimeter inverse in the aldehyde to carboxylic band. Carboxylic acid. The infrared absorption spectra of carboxylic acid exhibits a number of absorption bands which are very helpful in detection of a carboxylic functional group. There is a very broad and intensive band in 3000 to 2500 centimeter inverse range due to OH stretching. This is clearly indicate the indication of strong hydrogen bonding than in alcohol, where the OH stretching band in the region 3600 to 3200 centimeter inverse. Another strong band appear around 1700 centimeter inverse, 1700 to 1880 centimeter inverse for aromatic acid and 1725 to 1700 centimeter inverse aliphatic acid due to carbonyl stretching. In addition, carboxylic acid also show a carbon oxygen stretching band at about 1250 centimeter inverse and bending band of OH near 1400 centimeter inverse and 920 centimeter inverse. Figure 1.1 depicts the infrared spectra of propanoic acid. Carboxylic acid derivative. As expected, the infrared of acid derivatives such as acid, chloride, anhydride, ester, and amides are characterized by presence of carbonyl stretching band. The exact frequency of a band depending upon the nature of a compound. Thus, acid chloride show a strong band at 1815 to 1885 centimeter inverse, while acid anhydride exhibits two strong band at 1840 to 1800 centimeter inverse and 1780 to 1740 centimeter inverse. However, in conjugation acid chloride and anhydride, these bands occur at 15 to 20 centimeter inverse lower frequency. Amide show carbonyl stretching band at 1690 to 1650 centimeter inverse. Saturated aliphatic ester give the carbonyl band around 1740 centimeter inverse alpha beta unsaturated esters. And aryl esters exhibits this band at 1730 to 1715 centimeter, while vinylic ester and phenylic esters show this band around 1770 centimeter inverse. Ester and anhydride also give two strong CO stretching band in region 1350 to 1050 centimeter inverse. These serve to distinguish them from ketone. Acid chloride show CCl stretching band in 800 to 650 centimeter inverse range. Amide show NH stretching band at 3500 to 3100 centimeter inverse and also NH band stretching around 16 centimeter. Unlike carboxylic acid, acid derivative do not any broad OH stretching band. This main feature of a spectra of acid derivative are summarized up in a table 1.1. Figure 1.11 show the infrared spectra of ethylene acetate. Amines. The infrared spectra of amines show characteristic absorption band due to NH stretching, NH band and CN stretching. The number of position of a band depend upon the classes while the amine belongs. Primary and secondary amines exhibit moderately weak absorption at 3500 to 3200 centimeter inverse due to NH stretching vibration. However, primary amines have two such band in the region while NH bond vibration. However, primary amines has a two such bond in a region while secondary amines show only one bond. Tertiary amines do not show any NH bond in their molecule and therefore they do not exhibit such band. Hydrogen bonding tends to the shift of NH band to lower frequency, but the shift is not as much as in case of hydroxyl compound. This is because the hydrogen bonding is in amines is weaker than that in a compound. Primary amines exhibits moderately strong NH bending bond at 1650 to 1560 centimeter inverse and nosto to 650 centimeter inverse, while secondary amines show weak band of this type around 1600 to 1500 centimeter inverse. The C and stretching band of aliphatic amines appear in a region 1230 to 1030 centimeter inverse. The intensity of absorption being weak. On the other hand, aromatic amine exhibits two strong bond at 1360 to 1180 centimeter inverse due to CN bond stretching. These bands may be used to distinguish between aliphatic and aromatic amines. The salt of amine such as hydrochloride show a broad band in 3000 to 2200 centimeter inverse region, which is typically of ammonia ion. The main feature of infrared spectra of amines are given in table 1.11. The salt of amines such as hydrochloric such as show a broad band in 3000 to 2200 centimeter inverse region, which is typically of ammonia ion. The main feature of infrared spectra of amines are given in table 1.11. Infrared spectra of N-butyl amine is shown in figure 1.12. Nitriles. The infrared spectra of nitriles are characterized by the presence of a C and triple bond stretching absorption band of 22 to 22 centimeter inverse of variable intensity. Conjugation with the double bond or aromatic ring shift the absorption of lower frequency. Nitro compound. The infrared spectra of nitro compound show two strong at about 15 to 60 centimeter inverse and 1350 centimeter inverse due to symmetrical and asymmetrical stretching of NO bond primary nitro compounds. Absorption at high frequency at the compared to secondary, while tertiary compound absorb at even low frequency. Conjugation of a nitro group with an aromatic move these band to lower frequency. For example, nitrobenzene show absorption band at 1525 and 1350 centimeter inverse. Interpretation of IR spectra having studies of characteristic absorption of various functional group. We given below a few useful tips for remembering the specific absorption region and interpretation the infrared spectra. Remembering the specific absorption region. For the purpose, the infrared for 4000 to 700 centimeter inverse may be broadly treated as a consisting of a four parts. First, the reason from 4000 to 2500 centimeter inverse is the absorption of CH-OH NH single bond stretching vibration. NH-OH bond absorption in the region 3300 to 3600, while CH bond absorption occur around 3000 centimeter inverse. Second, the region from 2500 to 2000 centimeter inverse corresponding to carbon triple bond, carbon nitrogen triple bond stretching absorption. The region from 2000 to 1500 deal with carbon double bond, carbon oxygen double bond and carbon nitrogen double bond stretching vibration. Carbonyl group generally occur between 1670 to 1880 centimeter, while ethylic double bond absorption generally plays from 1660 to 1680 centimeter inverse. The region below 1500 centimeter inverse constitutes the fingerprint region, where is a number of complex absorption band appear due to different kind of carbon single bond, carbon oxygen single bond, carbon nitrogen single bond, carbon halogen single bond vibration. Interpreting the infrared spectra, the following point should prove very helpful in interpretation of infrared. First, allows start with the high frequency end of spectra. The absorption band due to most of the symmetrical vibrational absorbed in the region above 1500 centimeter inverse. The region below 1500 centimeter inverse is used only for the confirmation of identical of a compound. Third, it is neither necessary nor possible to interpret each and every possible band. Most of the information is obtained from a relatively few bands. Fourth, the relatively evidence is always more reliable. What this type means is that the absence of a characteristic absorption band of bond or a group is sure guaranteed of the absence of the particular bond or a group. For example, if there is no absorption band in the region 16 to 18 centimeter inverse, the carbonyl group must be present in a group. Overtone and coupling peaks. Before concluding this discussion, it may be pointed out that the actual appearance of IR spectra become rather complicated due to the presence of certain absorption band in addition to the band due to fundamental vibrational mode of the various bonds. Such additional bands are called overtone and coupling peaks, but these additional bands are much lesser intense from fundamental bands. Overtone. These are high frequency bands which may occur at or nearly integrated multiples, such that 2 times, 3 times, etc. of a fundamental band frequency. The overtone which appear at double bond is known as second overtone and so on. For example, in the spectra of carbonyl compounds, such overtone are present in a range of 32 to 35 centimeter inverse, which is 2 times the characteristic absorption frequency of a carbon double bond oxygen stretching vibration. Coupling peak. These are additional band which result for the formation of a two foundation vibration frequency by these additional or subtraction for two fundamental frequency A and B. Additional band are appear at A plus B centimeter inverse, while difference band are appear at A minus B centimeter inverse. But only certain combination of a coupling vibration are allowed by consideration of a quantum mechanics. Moreover, intensity of these band is very low as compared to fundamental vibration. Fermi resonance. Usually the overtone and combination band are much lesser intense than the combination band. These is transfer from the fundamental vibration to the additional vibration. This increase the intensity of a overtone or a combination band. This mechanical coupling between fundamental band and additional band is known as Fermi resonance. This is quite often observed in IR spectra of a carbonyl compound. IR spectra of some simple molecule, as particularly illuminated of interpretation of IR spectra. Let us now identify the significant absorption band in the spectra of some special molecule. First, IR spectra of acetic acid in figure 1.13. The important band in the above spectra are as follows: 3030 centimeter inverse, a broad band of hydrogen bond OH stretching of a carboxylic acid. 1710 centimeter inverse, carbonyl stretching of a saturated chain carboxylic acid. 1280 centimeter inverse, carbon oxygen stretching of a carboxylic acid. 945 centimeter inverse, oxygen hydrogen bending of a carboxylic acid. Second, IR spectra of benzaldehyde. The important band in the presence of spectra may be identified as follows: 3080 centimeter inverse, carbon hydrogen single bond stretching of aromatic ring. 2860 centimeter inverse to 2775 centimeter inverse, carbon hydrogen single bond stretching of aldehyde. 1700 centimeter inverse, carboxyl stretching of an aromatic aldehyde. 1595 centimeter inverse, slightly double bond stretching of aromatic ring. 745 centimeter inverse to 885 centimeter inverse, band characterize the aromatic mono substituted CH deformation. Application of IR spectroscopy. The infrared spectrum is a highly characterized property of a substance, and the examination of the infrared spectra can add chemical investigation in many ways. The important application of infrared spectra are as follows. First, the identification of substance. Infrared spectroscopy is very often used to establish whether a given sample of an organic substance is identical with another or not. Due to large number of absorption bands found in the infrared spectrum of organic compounds, the probability that any two compounds will produce identically spectra is practically zero. This means that if two substances afford identical spectra under a similar condition of measurement, they must be samples of the same substance. However, the condition of recording the spectra, such as the physical state of a sample, solvent, and use and concentration of solution, must be the same, because a substance may produce appreciable different spectra under different set of conditions. It may be noted that the infrared spectra of two enantiomer compound take under the same condition are exactly identical. In other words, infrared spectroscopy failed to distinguish between an enantiomer. Second, different determination of functional group and molecular structure. Infrared spectroscopy is very harmful in determining the molecular structure of unknown spectra. For an examination of a position of absorption band in the spectra, it is often possible to establish the nature of a group present in a molecule. For example, if a spectra contains a strong band at 5.82 micrometer, the compound concerned must contain a carboxylic group. The information in conjugation with the study of other band may tell a greater deal about the structure of a compound. It is obvious that if a spectrum does not contain an absorption band typically of a particular functional group, the substance does not contain the group. Third, study the progress of a reaction. Progress of a reaction can be readily followed by the examining spectra of some portion of a reaction mix with the draw from time to time the rate of disappearance of a characteristic absorption band of a reactant group, or the rate of increasing absorption band due to the formation of some product help in studying the progress of a reaction. For example, the gradual disappearance of a hydroxyl strength frequency at 2.74 to 2.78 micrometer, and the consequent appearance of carboxylic strength frequency at 5.68 to 5.95 micrometer can be used to study the oxidation of an alcohol to a carboxylic acid. Similarly, the systematic interpretation of IR spectra can be very useful in determining whether a reaction has occurred to give the expected product or not. Fourth, detection of impurities. If it is possible to determine whether a given sample of a compound is pure or not, provided the reference spectrum of a pure compound is available. In contrast with the spectra of a pure compound, the spectra of an impure sample is blurred and not so sharp and contain many extra bands. For example, the presence of ketone as an impurity in an alcohol lead to rather poor spectra having additional absorption band due to carboxylic group. Some example of use of infrared spectroscopy. To illustrate the use of infrared spectroscopy in structural analysis, a few simple examples are given below. Example 1, indicate the expected important absorption region in the IR spectra of following compound: isopropyl alcohol, dimethyl ethers, and toluenes. The important absorption band expected in IR spectra of isopropyl alcohol are as follows: 32 to 3400 centimeter inverse, a strong and broad band due to hydrogen bonding of OH stretching. 2850 to 2950 centimeter inverse due to carbon hydrogen stretching. 1000 to 3300 centimeter inverse due to carbon oxygen stretching. Second, the important absorption band expected in IR spectra of dimethyl ether are as follows: 1060 to 1150 सेंटीमीटर इनवर्स ड्यू टू सी ओ स्ट्रेचिंग. 2850 to 2950 सेंटीमीटर इनवर्स ड्यू टू कार्बन हाइड्रोजन स्ट्रेचिंग ऑफ मिथाइल ग्रुप. Third, the IR spectra of toluene would be expected to have the following important absorption band: 2850 to 2950 सेंटीमीटर इनवर्स ड्यू टू कार्बन हाइड्रोजन स्ट्रेचिंग ऑफ मिथाइल ग्रुप. 3000 to 3100 सेंटीमीटर इनवर्स ड्यू टू सी एच स्ट्रेचिंग ऑफ एरोमेटिक रिंग. 1500 to 1600 centimeter inverse due to slight double bond of aromatic ring. Thank you. This chapter is complete.